Hello, my name is Marzieh. I am a PhD student from Pompeu Fabra University. In this paper, we studied how machine learning may be used to increase the effectiveness of a criminal recidivism risk assessment tool named Risk-Envy without introducing undue biases. Risk-Envy is a risk assessment tool that was introduced as a multi-level risk assessment protocol for violence prevention in the Catalan prison system in 2009. This protocol is applied multiple times during an inmate's period in prison. The official recommendation is to do risk-envy evaluations every 6 months. In each risk-envy evaluation, the inmate is interviewed by professionals, and risk is determined for the inmate relative to some outcomes: self-directed violence, violence in the prison facilities, committing further violent offenses, breaking prison permits, and a fifth score that was introduced more recently for general recidivism. In this study, our aim is to obtain more efficient and fair recidivism risk assessment tool. So let's review algorithmic fairness in some risk assessment tools so far. In seminal research done by investigative journalism organization ProPublica, it was concluded that the widely used Compass risk assessment tool is biased against African American defendants. A follow-up study analyzed the fairness of Compass in terms of predictive parity and found that Compass outcomes systematically overpredict risk for women, thereby indicating systemic gender bias. However, the findings of the ProPublica study were rejected by Northpoint, the Compass developer, claiming their algorithm is fair because it is well calibrated. And in this report, it is shown that the Compass risk scales exhibits accuracy, equity, and predictive parity. In comparison, other studies have shown that some risk assessment tools such as the PCRA, SABRI, and the YLS CMI do not exhibit racial bias in the recidivism prediction. Also, in a study focused on SABRI, it is shown that although ML models could be more accurate than the simple summation used to compute SABRI scores, they would introduce discrimination against some groups of defendants. In general, it is impossible to maximize fairness and accuracy at the same time. Also, there are many different definitions of algorithmic fairness, some of which are incompatible with one another. It is impossible to satisfy all of them simultaneously, hence there are necessary trade-offs between different metrics. In this regard, some studies try to mitigate potential algorithmic discrimination by satisfying equalized odds or, in other words, avoiding disparate mistreatment along different sensitive groups. In addition, due to the importance of the calibration in risk assessment tools, some previous work has also tried to minimize error disparity across groups while maintaining calibrated probability estimates. So in this work, to see the effectiveness of machine learning in comparison to the Risk-Envy protocol, we obtained a ML-based model to predict violent and general recidivism using some features consisting of demographics, which is gender, nationality, and age at the time of the last evaluation, a subset of selected risk items of the Risk-Envy evaluation using a feature selection method, and the average violent recidivism or general recidivism score from the first to the last Risk-Envy evaluation. So results in terms of AUC error rates, GFNR and GFPR are presented and compared with the existing Risk-Envy protocol in this table for both violent and general recidivism prediction. So according to these results, ML models with an AUC of 0.76 and 0.73 shows more accuracy compared to Risk-Envy protocol in predicting violent and general recidivism. And however, the difference is very small between the accuracy of ML models and Risk-Envy, and it is surprising considering that Risk-Envy was not computationally optimized for predictive accuracy. As well, ML models show less error rates in terms of generalized false positive rate and generalized false negative rate, and more F score compared to the Risk-Envy. By GFPR, or generalized false positive rate, we mean the probability of detecting recidivism for the cases who do not recidivate. And GFNR, or generalized false negative rate, means probability of failing to detect recidivism risk for cases who do recidivate. Then, by fairness analysis of the models, we show that algorithmic discrimination can easily be introduced between groups such as national versus foreigner or young versus old. So in the result table here, we can see biases in colored circles, as can be seen in both general and violent recidivism predictions. There are more disparities in terms of GFPR error, which are shown in red circles, compared to other metrics. So in order to mitigate this bias, we applied a method in which a single error disparity in terms of GFPR is minimized, while calibration is maintained across groups. Calibration means that the output of the classifier is not merely a score, but an estimate of the probability of the outcome. When we talk about fairness across two groups, it is important that this calibration condition holds for the cases within each of these groups as well. Because if the risk tool is not calibrated with respect to different groups, then the same risk estimates carries a different meaning and cannot be interpreted equally for different groups. So here we can see the results. Obtained results show that the bias mitigation procedure can reduce GFPR disparities across groups. So as a conclusion, we can say that using ML-based models in this study, we obtained a slightly more accurate results compared to risk-MV. Although this improvement in accuracy by ML model would be insufficient on its own to support its introduction as a risk assessment tool, a key element of ML models is their flexibility. An ML model can be retrained with newer data and incorporate new factors as the population of inmates changes and more data on recidivism becomes available. So then we analyzed algorithmic fairness of the models and found some disparities in terms of GFPR. By studying differential treatment of risk-MV and ML models across different groups, it can be stated that depending on the desired metric and groups, machine learning and human expert can lead to different but comparable results. An advantage of ML model is that the emphasis on different metrics can be changed during the modeling as legal or policy changes are introduced. Then using a bias mitigation method, we could minimize GFPR biases while calibration was maintained across groups. Finally, when introducing ML-based risk prediction in an application, improvements in accuracy need to be carefully contrasted with potential algorithmic discrimination, and it is very important to apply algorithmic bias mitigation procedures to minimize the disparities across groups. Thank you.
Thank you, Mrs. Marzieh. We have a question here for you. Do you think the AI regulatory framework proposed by the European Commission last April could affect the application of your model?
You mean according if in with respect to fairness, you mean the fairness definitions? Yes. I don't know if this question is related to the fairness definition of GDPR.
The only information that I have is the one that they sent me. So you can comment about it. You don't have to specifically answer this question.
Yes. So yes, yes, it is. Generally, it is because one of the most important things regarding algorithm and machine learning in society is this considering this discrimination that is inside the algorithms. So this is one of the important things that, and the GDPR considers this a lot. And but the thing is that something is different, not different, but in computer science, which is my field, in comparison to law, we have we have the same meanings, but with different definitions, in fairness. So maybe the expressions should have a common language in both law and computer science, but the goal and the aim is the same. I mean, the meaning and concept is the same, but some common language should connect them together, like computer science and law expressions.